This video is going to cover the last of the reactions on aldehydes and ketones. The first reaction we're going to talk about involves aldehydes and ketones reacting with a primary amine. Both of these will create the same new functional group, what is known as an imine, in which a carbon is double bonded to a nitrogen. Notice here, it is trading its 2 bonds to oxygen to its 2 bonds to nitrogen, and the nitrogen is trading his 2 bonds to 2 hydrogens to 2 bonds to the carbon. So a nice little trade. The same functional group will result if you use a ketone. Same thing here, you just have a hydrogen on the carbon with an aldehyde versus 2 R groups on a ketone. This mechanism is pretty complex, but we'll go through it now. This is going to start with the same arrows we saw with Grignard's and all the other nucleophiles we've talked about. In this case, we don't have a negative charge. We have a lone pair on the nitrogen, which is enough to make it nucleophilic at the electrophilic carbon of the carbonyl. Just like with our other reactions, as soon as we push those lone pairs into the carbonyl, electrons need to be pushed out onto the oxygen. At this point, you have a protonated nitrogen and a negative charge on the oxygen. You can draw this arrow coming from the hydrogen onto the nitrogen. I've seen some textbooks do that. You can also add it from the acid source. This step needs to be done as well. You have a positively charged nitrogen, so if you don't use your O- to take it, you need to show a base pulling off this hydrogen. This will regenerate your acid that you used in the last step. At this point, you've now created a tetrahedral intermediate, and you're looking at an OH versus an NHR group. Which one of those is going to get protonated? Well, if we protonate the nitrogen, we're going to end up going back to what we had before, an aldehyde or a ketone. So if we protonate the OH group, what will that end up leaving us with? At this point, we'll pull off a hydrogen from our newly acquired acid source. This will then create water, which will be able to leave. Notice our arrows again. Instead of having the water leave, creating a carbocation, the lone pair on the nitrogen pushes down, kicking out the water. Your next step would be removing the last hydrogen from your nitrogen because it has 4 bonds, giving you your imine. So to me, I think here it's really important to remember what functional group you're making, because as you try to go from the double bonded O to the double bonded N, it's really keeping track of what's happening with the hydrogens at each position and what do you need to do to alleviate positive charges on each atom. The intermediates in imine formation are often unstable, and we can look at the difference between our tetrahedral compounds where we have our aldehydes or ketones versus our unstable tetrahedral intermediates. At the top, we only have 1 functional group that can be protonated. In the bottom, we now have 2. So we actually could see the OH pick up a hydrogen, we could see the nitrogen pick up the hydrogen. In order to complete this reaction, forcing imine formation, you want to be able to remove or limit the amount of water that's in your sample, since water is going to be your leaving group. Limiting the amount of water will help make the nitrogen push out water as a leaving group. This reaction would be the reverse, right? Starting with an imine, adding water, also with acid, going to our carbonyl source. At this point, notice it's not trace acid. There's a full equivalent here, meaning your amine at the end is going to be protonated, removing the lone pair, meaning this is not reversible because the nitrogen has lost its ability to act as a nucleophile. The other reaction we will talk about is an aldehyde or ketone with an alcohol. These are also acid catalyzed. Having your acid work as a protonation step, just like with the last one, where we normally saw negative or anions for nucleophiles, we have another neutral nucleophile here, which can add once. And also, if time and heat is added, you can end up adding 2 equivalents of these. Adding one equivalent is known as a hemiacetal. It's very difficult to isolate these because it's tough to tell when you can have one full equivalent added. So a second equivalent is usually added, making a full acetal. Let's look at the mechanism for acetal formation. This mechanism actually will have a different first step, and the reason why is we have a poor nucleophile. In order to make our alcohol into a better nucleophile, we're going to give it a really strong electrophilic carbon. This will result in a poor nucleophile being able to act as a nucleophile. The first step will be the oxygen picking off the hydrogen from your acid. I haven't drawn it here, but this structure has a resonance structure which places the positive charge on the carbonyl carbon, allowing for a weak nucleophile to add. This step is, however, the same as our other arrows for all the other mechanisms here, where your nucleophile is adding to the carbon and pushing electrons out. At this point, you have a tetrahedral intermediate. Before you can move forward with the reaction, you have an oxygen with 3 bonds. This oxygen has a pKa relatively close to strong acids, so before you move any further, you need to make sure you're deprotonating this with whatever base you have. Could be the conjugate base from your acid. At this point, you have an intermediate. This is where you have an hemiacetal. You can either protonate the OH or the newly added OCH3. If we protonate the OCH3, we'll end up back to where we started, and that's why these arrows are reversible. In order to continue with the reaction, we're going to have the OH pick up another hydrogen, and I've included that picture here. This now creates a great leading group, meaning our lone pair on our methoxy group can push down, kicking out water. So this is very similar to what we saw with amine formation. At this point, we have a positively charged oxygen, again with 3 bonds. This arrow should look very familiar. We have a resonance structure placing a carbocation on the carbonyl carbon, allowing our poor nucleophile to come in, push electrons out onto the OCH3. The rest is just hydrogen workup, right? Making sure that you have a neutral species, so the base is going to come and pull off the hydrogen from our newly added alcohol, giving us our final piece, an acetal. You can also push this the other direction, starting with an acetal, using water as a way to make sure it's the nucleophile, constantly finding these pieces, using water as a way to regenerate your starting material of an aldehyde or a ketone. I do not show you this mechanism, but since it's the reverse from the last step, you should be able to draw it.